We got a magnet, we got spacers, we've got a couple of wheels with a toy car mounted on it. Okay? And on the rear end of that toy car, we've mounted another magnet. And the toy car, of course, has to have them and stuff. Okay. Toy car. Magnet. Okay. Release. Okay. The potential energy, term I haven't defined yet. Potential energy of the magnets at the given spacing. You can't just talk about the potential energy of the magnets. You got more potential energy if the magnets are closer, right? Okay? So you got to talk about the spacing. The magnets at a spacing give you a potential energy. And more details we could use with the magnets and their orientations, but you get the idea. Okay, and the orientations I've already set up for you. Changes to kinetic energy. Okay? Changes kinetic energy because of the repelling force. Okay? That is the average kinetic energy is the average of your net force times delta x. Okay? And the average of your net force, incidentally, how do you get the average value of a function?
Just plug two numbers in and get the average.
It's only if you have a linear function. This function ain't linear.
Derivative of it.
Huh?
The derivative of the function.
No, derivative's not going to help you with the average value.
Derivative is instantaneous.
What's the definition of the average value of a function for calculus? See what I mean about people coming out of calculus and not knowing the fundamental ideas? That is absolutely fundamental. It's not the most fundamental idea, but it's right in the next category. Nobody understands that. Nobody understands tangent lines. Nobody understands differentials, okay? Nobody even knows what a derivative is. They can calculate them if they happen to remember the formulas, but that's about it. Now, you guys probably know a little more of that, but I'm talking about what I generally see when I teach a course that requires knowledge of calculus, and there's very little knowledge of calculus. Although, you know, you scratch the surface and review a little bit, and you find, yeah, there is some. But, you know, the basic ideas, the forest gets lost for the trees, which is typical. It kind of did with me, too. I probably thought about it a little more than most people do, though. So, still, And I was by no means exemplary with that, but I wanted to know, and I kept coming back at it. Okay, so you have this, right? And also, that's the definition of the average value of the function. You divide the integral by the length of the interval over which you're integrating. If that's not something you've at least seen or struggled with a little bit, it's not that big a struggle. Okay? Then, again, something's missing. So we'll maybe talk a little bit more about that. You should review that definition of the average value of a function. You should really understand this. Because right now, you just needed it and you didn't have it, right? So we just had to waste 5 minutes of your life and something you're supposed to know. And if this didn't refresh you, you never knew it, okay? You might have been able to answer a question about it if it was phrased just right and you recognize the words, but you didn't understand it. So go back and understand it, okay? Now, okay, there's your repelling force. Anyhow, and this experiment will incidentally help reinforce this. But go back and review it, okay? Okay, so, and actually I've misstated a couple of things here, so I'm going to have to, well, let's see. Okay, work done by the repelling force plus the work done by friction is the work done by the net force, isn't it? Okay? And y'all picked up on friction. I did just ask what's happening with energy. Why does this thing lose its energy? Is it friction? Well, it's the work done by friction. Friction's in that direction. We're moving in that direction. So friction does negative work, right? And the magnet does positive work. Now you think, you separate the magnets by, you don't have to separate them that far before you can't even observe the force. Okay? Doesn't mean there's not a force. No matter how far those magnets are apart, there is a force, however minuscule and however ineffective on anything. Okay? But what we're looking at now here is okay, from release to rest, on the interval from release to rest, what's the work on that interval? The work done by the net force on that interval. And what do you know about the work done by the net force?
It's equal to the repelling force plus the work by friction.
Exactly. And what else do you know?
It's equal to the displacement times the net force.
Or the integral of the net force over the displacement. We haven't talked about the integral definition, but you kind of know that. Okay? Okay? Well, what else is it equal to?
1/2 of the mass times velocity squared. Well, no, that's just kinetic energy. It's 1/2 of the mass times velocity final minus 1/2 the mass times velocity initial.
The squares of those velocities. In other words, change of kinetic energy.
Yeah.
That would have been the succinct answer, but that was a good answer. Okay? Well, don't be dull than that.
I've tried it a couple of times and it works out. Of course, when it's for area, it's more damage also.
So two answers.
One male.
And delta KE just stands for, 1/2 MVF squared minus 1/2 MV naught squared, right? Okay? So del W nets, delta KE, del W nets, this plus this. So what do you conclude?
The change in kinetic energy is equal to the change in the work done by the repelling force and the work done by friction.
Okay, what else can you tell me about delta KE from release to rest? Everybody's having too much fun. I'm gonna just gently.
Well, that one teacher that
I
slammed
can't even
earlier.
tell what room that's coming from. It's not right next door. It's down the hall somewhere. Okay. And they've got the door open, I think. I mean, if they didn't, the whole room would explode, so I guess I have to. Okay, so that's a conservation of energy. Okay, so anyhow, what do we got here now? What can you tell me about the delta KE on this interval? Well, what's the status of the system at the beginning of this interval?
It has kinetic energy.
Huh?
It has kinetic energy.
Okay. Why does it have kinetic energy?
Because it's moving.
Now, at the beginning of this interval, what starts the interval?
The release.
At the instant of release, how much kinetic energy does it have? It doesn't have any. It hasn't had time to build any. At the instant of release, right? So at the instant of release, kinetic energy is 0. Okay? What about the end of the interval? It's at rest. Kinetic energy is 0, right? Okay? Okay, change in kinetic energy is 0. Okay? Okay? So, work done by the repelling force is equal and opposite to the work done by friction. Okay? And the work done by friction, of course, is negative because the car's moving this way and the force is this way, so you multiply in opposite signs, right? Okay? Okay, well, okay, we're going to make a definition now. let me ask, by how much does the potential energy of the magnets change during this interval?
By
Does potential energy of the magnets increase or decrease? Decreases. And why do you say decreases?
because you're saying it changes to kinetic energy.
No, I just said that. Don't believe
Decreases.
anything I say.
With extra magnets being added in.
Okay, well,
extra distance.
okay.
It decreases with the distance from, or in between the two magnets,
Why?
because the two magnets are what is causing the force.
Okay. Okay, look. Got these things pushed together. It's really pretty tough. Okay, I'm gonna have to. Oh, that's a little better. Okay. Now, is there more potential energy here or here?
When they're closer together.
Why? Because I was straining harder? Or because if I release them from here, I get more kinetic energy than if I release them from here. That's why. Okay? Potential energy is the potential to do work. Okay? And since the work done is equivalent to the work done by the net force, at least, is equivalent to the change in kinetic energy, if the net force is just a magnet force. Okay? Then if we release, you know, you can make that connection. It just comes down to intuitively, this intuition thing that we need, so we understand what the formulas are telling us and understand what formulas to use and so forth, right? So we don't like use the equations of uniformly accelerated motion for simple harmonic motion. I keep mentioning that. I hope I don't see that. Okay? Again, because we get more kinetic energy out of the system at this proximity than at this proximity. This situation has more kinetic energy than this, right? Well, that means that as the cart, or as the two magnet system, which is what we're really studying, the cart's just one of our mechanisms for studying it. If the two magnet system has a certain potential energy here, then when it gets here, it has less potential energy, right? I mean, it still may be moving here in the experiment, maybe not. But, you know, eventually we get to a point where it's at rest. Well, there's still a little bit of potential energy here, but it's really trivial, and we're going to kind of assume that's negligible compared to anything we can measure, at least in this experiment. Okay? So the point is then that potential energy decreases with increasing separation. Okay? Intuitively, that happens because or since we get less kinetic energy when releasing from greater separation. Okay? Does that relate to what I said? Okay? So, if potential energy is the amount of kinetic energy we can get out of the system, or the amount of work we can get out of the system, the amount of energy we can get because of the proximity or the position of the system. Okay? We can say that. Now, since the potential energy decreases, the separation. Then LW repel, the work done by the repelling force from release to rest is equal and opposite to the change of potential energy. Okay? That's assuming that the potential energy at the final separation is negative. Okay? Make sense? Okay, so the change of potential energy is equal and opposite to the work done by the repelling force. Okay? Now, big deal, because this leads us directly to our definition of potential energy. And I only define change in potential energy because potential energy is always defined relative to some point, and we have to decide what point we use to define change in potential energy. So, okay. I'd have to leave a little too soon. Okay? Conservative forces are path independent. Okay? Friction is not path independent. When that cart goes from the path from here to there, friction acts in this direction. If the cart was to come back, friction would act in that direction. So friction depends on in what direction you're moving. Okay? Friction isn't. Okay? Magnetic forces are. The magnetic force between those magnets doesn't depend on what direction you're moving, only depends on how far the magnets are apart. Okay? So are gravitational, electrical, and ideal elastic forces. Rubber bands exert an elastic force. It's not really path independent. Okay? We've got this hysteresis type loop. And if you stretch a rubber band, then take it back. There's a difference in the force. Thermodynamic. Mostly thermodynamic based. But ideally, like a really good spring, well, if you flex it, it heats up. Okay? So it's not completely ideal, but it can be very close. Okay? So the reason this is important is gravitational forces. Okay? You know, everything we do on Earth, okay, gravitational force is a conservative force. Path independent. I lift something, I lower it, I toss it. As long as I don't get significantly further from the center of the Earth, the force on it, or move too far along the curved surface, the force doesn't change. If I toss this chalk to you, the force ain't going to change by any non-negligible amount. Or direction, even the magnitude direction of force. Electrical, you know, static electricity, all kinds of other things in steady state conservation. Okay? And force of a good spring. Let me lay this definition on you. Okay? So, this is something I never want you not to be able to recite. So once this is out of your sight, make sure you can recite it. Okay? It's really pretty foundational.
So therefore, the net force is equal and the same as the repelling force.
Well, for the magnet, that would be the conservative force. That's not the net force. The net force is the conservative force plus the frictional force in this case. Gravity being opposed, equal, and opposite on a horizontal surface by the normal force exerted by the table. Now, if you're on an incline, then you got a potential energy change because of gravity. Okay? And you're going to have some problems that ask you to actually calculate that. Okay? So there it is. Do the experiment.